Yeah, it might be that we get like rather sometimes it can be that it starts to bubble. The ceiling, not when it is. But it's interesting that I only that's not the option. Yeah. Oh, yeah. All right, well, we'll start the last section with Sarah Jane talking about chromites and PGE-bearing layered intrusions.
No? Okay. None of the buttons work. Oh, great. Thank you.
Yep.
Okay, so I'm going to talk to you about the composition of chromites from PGE layered intrusions. And to do this, I'm going to compare the composition of chromites from PGE-bearing intrusions with chromites and picrites, and the locations we're going to talk about, which I don't know why. Never mind. The locations we're going to talk about, you probably all know where the Bushveld is, the Great Dyke, Stillwater, and then Alexo is a chromitite that's in lower green schist or prehnite pampelite facies, and the Emishan flood basalt. Why? Well, chromite is the only source of chrome for 40% of the world's chrome. And it comes from the massive chromitite layers that are about 1 meter thick in layered intrusions. So what we want to ask here is, can the composition of the chromites tell us anything about the composition of the magmas that form these intrusions? Is there something special about these intrusions and their composition? The next thing is, given that the cotectic proportions of chromite to silicate in a normal situation is 1 to 2%, how do the massive layers form? And remembering we're talking about PGs, this is the platinum symposium, so we've got to talk about PGs. Whole rock, the plot, if we look at a plot of whole rock compositions for PGs and chromite layers, and we also look at the same time as the composition of, oh, no idea how to get this. Anyway, if we look at the same time as the composition of the trapped liquid estimates, that's the green line, you'll see that in general, chromites are enriched in osmium, iridium, ruthenium, and sometimes osmium, iridium, ruthenium, and sometimes rhodium. So we can ask, do the IPG elements partition into the chromite, or are we crystallizing PGM minerals? Also, sometimes the chromite layers higher up in the intrusions. Sorry, I'm not, should I speak more loudly? Are you hearing me at the back? Yeah. Okay. Sometimes the chromites from the upper parts of the intrusion are enriched in palladium and platinum, if we're lucky. Indeed, as we all know, the world's largest platinum deposit, the UG2, at the Bushveld, contains very little sulfur and yet contains all this platinum and palladium. So what is it about chromite that is concentrating platinum and palladium in some cases? So we have to consider various things based on the experimental work, and is true for almost any phase reaching saturation. We need to consider the intensive variables, pressure, temperature, oxygen gasicity, composition of the liquid, as discussed by James this morning. But then we have to think after the chromite crystallizes, there's quite a long period above the solidus, depending on which sort of magma we've got. But in a chromitite, can be going from 1500 to 1000 degrees, and the chromite's just sitting there and possibly reacting with the liquid. So this is a plot of chromite from the Emershan province, which has got a reaction rim around it that is more iron rich, and you can see the trace element distributions throughout it. Generally, most of the trace elements go up in the magnetite. So you're seeing frozen there a reactional chromite forming. So we need to consider what happens after the chromite crystallizes as well, if we're going to talk about the composition. And then, of course, as pointed out by Steve some time ago, there's complex changes during metamorphism. Now, I'm not going to be talking about metamorphosed chromites, but if you've got metamorphosed chromites and they're above green schist facies, it's horribly complicated and it's not easy to interpret. There's this paper by Steve, and there's also a very nice, elegant paper by Guista, who talks about how the iron and the chrome change as you go, and the different sites they use as you go from chromite to magnetite. And on the triangular diagram there at the bottom, you can see you move from the red box up to the blue box as the metamorphism progresses. In general, during metamorphism, the chromites tend to get transformed to magnetite eventually. Right, next, first we're going to consider the composition of the alexochromitite chromites. Why? Because it's rapidly chilled, so we can limit the amount of re-equilibration between crystallization and solidification. And we have a range of liquid compositions because we have the olivine spinifex and a clinopyroxene spinifex flow. And the metamorphic grade is low, so we don't have to worry about the metamorphism. And then we'll consider the layered intrusions. Great Dyke and Bushveld are not metamorphosed. Stillwater is lower green schist, so metamorphic effects I hope are limited. And then we'll compare the massive chromite layers with disseminated to try and limit the amount of subsolidus re-equilibration we've got to worry about. So first things first, always check that that little black thing you've analyzed is actually a chromite. A lot of the time, recently I've been receiving papers that are not actually chromite, and they go on and on and on about chromite. It's not chromite, so make sure they're all chromites before you start. Now, which elements are we going to consider? There are two sites in chromite, the chrome site and the iron site, +3 and a +2 site. Fortunately, the +2 iron in the tetrahedral site is roughly the same size as the chrome. So any iron between about, they're both 0.63, 0.615 angstroms. So any iron between the size of 0.5 and 0.72 will fit into the lattice. And if they're a +2 or +3 iron, they're going to do well. There's also the question of crystal field energy, which I'm not going to bother you with too much, but that has a subtle effect on which ions are going to go in first. So chrome gains the most by going in. Hallelujah, makes a chromite. Interestingly, nickel likes to go into the chrome site because it gets lots of crystal field energy, even though it's a +2 ion, is in the +3 site, and so on. Don't worry about that too much. You can always look at the PDF if you want to. but that's just for those people who like to know about crystal field effects. So for the chromites and the layered intrusions, we can quantitatively determine +2 ions that go into chromite, magnesium, manganese, nickel, cobalt, zinc. The +3 ions, aluminium, gallium, vanadium, ruthenium. Scandium is a little bit too big. That's why it's in italics, but we can determine it. So we'll talk about it a bit because it can keep a track of what's happening with the pyroxenes. And titanium is a +4 ion, obviously slightly off. It's slightly incompatible with chromite, but you do see some titanium. We're also going to mention iridium, rhodium, because they're IPGs, and tin, zircon, and hafnium, but they're just semi-quant. So, and one can't put too much pressure on them for interpretation. And platinum, palladium, and gold, they're always less than detection limit of, that should say 10 ppb, sorry, not 10 ppm. So they're less than 10 ppb, not 10 ppm. Typo. Right. So this is a plot of chrome number versus iron number, a classic chromite plot that people do all the time. And what I've got here are the compositions of the chromites from the olivine spinifex flow in red, and the different textures are different symbols. Don't worry about that too much. And blue is a clinopyroxene flow, which would have formed at a slightly lower temperature. And then I put, taking the hyaloclastite, the pure glass with it's got no chromite inclusions at all, as a starting liquid. And I've used the oxygen fugacity of FMQ, which has been based on the vanadium content of the chromites. You can use vanadium, if you know the vanadium content of the liquid, to estimate the oxygen fugacity. You could also use Fe3 over Fe2 plus a la Bellhouse. The problem there is, of course, iron can be, as we'll see later, can re-equilibrate a bit. So that might not give you the right answer. Right, so if we use melts and we have fractional crystallization, you see those little dots going down the screen, that is what melts predicts should happen. So if you project across there, can somebody show me how to get the laser thing going? Because it really would be nice to be able to point at these. Sorry, be a nuisance. Thank you. Hallelujah. Okay, so if you trace the temperatures that the chrome number gives you, they begin at 1500 in the olivine spinifex flow, and they might be down to 1400 in the clinopyroxene flow. Makes perfect sense. But when you look at the iron number, everything's horizontal, and the iron number is giving us 1200 to 1157, which those of you who work on chromites, it's perfectly normal, seen that, done that. But if you're new to chromites, it's important to know that the +3 ions will give you a higher temperature and freeze in what's going on at a higher temperature than the +2 ions. This is about diffusion, of course. +2 ions diffuse more readily than +3 ions. Although this has been known for some time, there's a long history of this. The recent experimental work, I found, well, I thought it was a nice paper. There's a nice chromite here where she's dissolved in her bononite in this case, and heated it up. And this is a section of the change in iron from the center to the margins. And you see, as you go through from the center to the margins, the iron 2+ starts to increase quite a bit, and the aluminium goes down, but particularly the magnesium goes down. Iron 3+ also goes up. Notice chrome is the last thing to change. So you can see there how it's being re-equilibrating with the liquid. Okay, right. So that's all very well. Most of you knew that anyway. Now let's look at the trace elements. So if we look at the spinifex flows, titanium versus chrome number, the olivine spinifex flow here, and then melts is giving you its estimate of what's going on with the little dots there. And that's the clinopyroxene flow in blue. It doesn't look too bad. The chromite is essentially following the melts prediction. For the other elements, melts will not give you an answer for the trace elements because it doesn't do the trace elements. You have to make some assumption as to what the D partition coefficient is for each element, but there's experimental work for this. So in this case, I've used 5 for the vanadium, and in the silicates, it's only olivine crystallizing, so it's approximately 0. It's a little bit more, but gallium the same, 3.5, scandium 0.2. The silicates do take a bit of scandium. And the olivine takes a bit of scandium. But in general, as the chrome number goes down, these elements are all slightly incompatible or strongly incompatible, so they go up. So the point here is the chromite is reflecting the composition of the liquid. Yep. Now the +2 ions, if you plot them versus chrome number, it won't work. For the obvious reason, the +2 ions are diffusing. So it's much better to plot them versus ion number. So here's manganese, and no, melts doesn't give you the number for chromite. You have to do that yourself. But he does put manganese in the olivine for you. Okay, but in order to match the manganese with the ion number, we're down again at about 1100. Zinc, cobalt. Notice all of these are increasing as the magma fractionates. Interestingly, nickel does not, and that, of course, is because nickel goes into olivine, and it's the bulk D that matters. So if you've got 98% olivine, 2% chromite coming out, and olivine has a D of 3 to 5, then it's going, the nickel's going to go down a bit. So in general, what we see is the +3, +4 ions give us what's happening at high temperature, +2, what's happening at slightly lower temperature. But they still tell you about the melt. What about the PGs? Now we get into more difficult territory. So here's the whole rock iridium, and that's the star here is the hyaloclastite, the liquid. The rounds here are the cumulate, and these are the various liquids, layers of the olivine, the spinifex flow. And if we use a bulk D of about 5, we can sort of model the iridium. Notice we're talking about only a couple of ppb here. So nugget effects, all sorts of things could make life complicated. You're getting close to the detection limits. So getting anything that looked interesting was helpful. If we go to the chromite, we're using a partition coefficient of 20 into the chromite. You do see iridium in the chromite, and this, the signal is stable. So it's not inclusions. It is actually in there. The same ruthenium, we have a D of about 80. This ruthenium seems to be slightly compatible. Rhodium, I wouldn't like to write home about that, but it seems to not change very much. But the detection limit's 0.01 ppb, and we're knocking around 0.02, so I'm not going to make a song and dance about it. But anyway, iridium, ruthenium, and rhodium all seem to have gone into the chromite and are decreasing. Platinum, palladium are less than the detection limit of 10 ppb. So I'm not the only one who's worked, or our group is not the only group that's worked on PGE and volcanics. In fact, you have another expert sitting over there in blue. You can speak to him anytime. Park. And there are other papers you can look up about PGE in chromite, volcanic chromites. Right. If we look at for the picrites, the Emerson picrites, it's more complicated, different localities. We have high and low titanium picrites. So what I've done here is titanium in the whole rock, titanium in the chromite, and you can see that they correspond. The more titanium in the whole rock, the more in the chromite, etc. So you see that the +3 +4 ions will give you the right signal. So volcanics indicate liquid composition is preserved, but +2 ions have re-equilibrated to lower temperatures. Layered intrusions have a much longer cooling period. So is there more re-equilibration? And we have to think about two phases. There could be liquid, which is percolating through our chromite layers. It could be a different liquid to the liquid that the chromite crystallized. And then, of course, there's subsolidus re-equilibration to worry about. Okay, I'm not going to dwell on that, just say that we have these massive layers in the lower parts of the intrusion. So the Great Dyke has the highest chrome numbers. That's the dots here. Sorry, the crosses here. Stillwater is all the blue crosses here, which tend to have the lower chromite numbers. And the Bushveld starts on the close to the Great Dyke and goes all the way through down here. That's the lower critical zone, upper critical zone, and here is the UG2 from the north. Marinsky is displaced over here. So we have to, the crystal fractionation would take us down here, no problem. But we can see there's quite a lot of spread over to this across on the ion number. So is this due to lower temperature re-equilibration? Of course, for re-equilibration, we've got a lot of things to think about. We've got these very thin seams like the E seam at Stillwater. Are they reactional or at the Marinsky? G chromite is nice, thick, a much thicker seam, but the host is Hartsbergite against peroxenite. Of course, we know there's lots of anorthosite in the case of the UG1 of the Bushveld, but the LG6 is in peroxenite. So we've got lots of different rock types, and we've got lots of different, the proportion of chromite to silicates vary, and the silicate enclosing the chromite varies. So there's quite a lot of things to think about here. So first of all, for Stillwater, what I've done here is plot the weight % chromite in the whole rock versus the concentration of the element in chromite. And what you can see here is the +2 ions like manganese, the lower the chromite concentration in the whole rock, then higher the manganese, and same for cobalt, zinc. Nickel doesn't change very much. So it seems that certainly manganese, cobalt, and zinc are re-equilibrating with the silicates or the trapped liquid. Nickel, perhaps nickel's not changing very much because olivine is the dominant cumulate phase, and olivine, of course, will be controlling the nickel rather than chromite. If we look at the +3 ions, we don't see much change either, except for the C chromite, where you can see that titanium, titanium for most of the Stillwater is around 0.4, 0.5. And then in the C chromite, we're getting up to 1% or so. The same, the gallium in the C chromite goes up. And of course, the question then becomes, wait a minute, is that because the C chromite has a different liquid, or is it because of the lower chromite content? Because of course now at Stillwater, I've got all the seams plotted on the same diagram. So what if we just take one zone? Fortunately for us, Langer has done this at the UG2 North in the Bushveld. And here he's got % chromite. In his case, he did modal versus the concentration of each element. And you can see that iron up to about 40% chromite doesn't change very much, but then it starts to go up very steeply as the amount of chromite in the rock goes down. And the same thing happens for manganese, cobalt, zinc, nickel. So we're not too surprised. We know +2 ions re-equilibrate. Sadly, so do the +3. So if we look at gallium, it's starting to go up when we get to about 30, 40%. Vanadium goes up quite strongly. The chrome goes down, titanium goes up, scandium doesn't seem to change that much, perhaps because pyroxene is present and pyroxene is controlling the scandium. So in general, we will have to say that when you've got less than 50% chromite in the rock, probably compositions have changed in a layered intrusion from their initial composition, sadly. If we consider this just a little bit more, we can look at the absolute gain or loss. And the elements, if we look at the absolute terms, we've lost chrome, manganese, magnesium, aluminium, about 12 grams, if you had 100 grams of rock. And then we've added a little bit of titanium and mainly iron, just in bulk terms. The trace elements, of course, they change as well, but they don't make that much difference to the mass in general because there's only a couple of thousand ppm or 100 ppm. If we look at this in terms of relative change, so how much it was before and how much it is now, not the absolute amount, now you'll see you're going from, you've lost 40% of your magnesium and you've gained 60% titanium. That's assuming that you have that the mass is stayed the same. Now, those of you who've had any experience with hydrothermal stuff will know that you should actually choose an element that you don't think has changed. So if we think chrome is the element that hasn't changed very much, because the experimental work shows chrome's the last one to go, and also there isn't so much chrome in the subsolidus material you're looking at, then you still get quite a large change, but using chrome as constant, magnesium, you still lost 30% of your magnesium and gained about 40% on the titanium side. So if the rock has less than 50 or 40% chromite, probably it's re-equilibrated in a layered intrusion. Another re-equilibration that you need to worry about is this is the margin between the bottom of the LG6 and the this is the silicates below the LG6, and now we're going in the LG6 and a little bit further into the LG6. So 1 centimeter below the bottom, we've got chrome numbers of 0.79 and titanium 1%, vanadium 3,400. Right at the contact here, you're still 0.7, this is a chrome number, titanium 3,500. So, and yet once you're 1 centimeter in, the composition is the same as 16 centimeters and higher. So the first centimeter of your chromite scene, and that applies to the top as well, is also can be reacted in some way. So you have to be very careful. You may have 50% chromite in that first centimeter, but still something, the ions have access to the silicates around them, underneath them, or the liquid that was passing through, whatever. So the first centimeter is not a good place either. So that's narrow seams are at risk of re-equilibration despite having greater than 50% chromite. The next question we can ask is, okay, we have interstitial minerals. Now, Steve showed us UG1 with 27% chromite. Most of the UG1 I've looked at has about 50% chromite or more. But in any event, you can ask yourself, does the effect of whether it's in pelagic layers or orthopyroxene, oikochrist, matter? Malta already looked at this for the UG2, for the Mg number and the chrome number, and he found there was no difference whether you had pelagic layers or OPX. And I can say from the limited data set we've got so far, it doesn't make any difference to manganese, vanadium, scandium, titanium, or gallium. So the fact you've got a pelagic layers oikochrist or a orthopyroxene oikochrist doesn't seem to make a difference. The chromite, as long as you've got more than 50% chromite, the chromite doesn't change that much. These are just element maps of the UG1 chromite to show you that we don't see any zonation. This is all lasering. We do see a little bit of alteration in the cracks for the manganese and zinc, but for most of the elements, there's no zonation. So we're not looking at reaction. Right, so that answers the subsolidus question. Stick to the things with more than 50% chromite and keep away from the margins. Unless you want to study reactional chromites. That's a different question. Okay, How do you make a 1 meter thick bed? And here's where the controversy always starts. Up to now, you've all been with me. Now, we're not so sure about this. So the classic model is we bring about chromite-only crystallization. Either we mix some new magma in, we increase the oxygen fugacity, we increase the pressure, although we've decided we're not going to do that with James. Maybe you put some water in. There's all sorts of things, but that's the classic model. The thing is that if only chromite is on the liquidus, then the elements are controlled by chromite. No brainer. And vanadium and gallium have partition coefficients of about 3 to 5. So if you crystallize only chromite, then those elements should go down as you go across a bed. This is the LG6. There's a chrome number, doesn't change over 1 meter. Gallium doesn't change over the 1 meter. Vanadium does not change over the 1 meter. So I don't know. If you're going to do chromite only crystallization, you're going to have to explain that. Okay, I got the idea off of James, by the way. I didn't brilliantly think of that all on my own. Okay, that's just the LG6 from the Neutkredach core. Now, what about the others? Well, this is at Impala, LG1, 1 meter. Again, does not significantly change on vanadium or gallium. UG2 at Impala does not significantly change. So we don't seem to see the necessary change for chromite-only crystallization. It doesn't rule out other processes, just not in situ chromite-only crystallization. There is a case where it does change, which everyone will, most of you will be aware of, and that is waterfall, which Tony Naldo did originally, but now Langer's done vanadium and gallium, and it goes up, not down. So it's the wrong way round. I don't know why it's doing that, by the way. I don't have an explanation, but there you go. Okay. How am I doing on time? Who's in charge? Chris, how am I? A lot of time. Okay. Oh, good. Right. So of the questions I asked in the beginning, we've talked about subsolidus. We've talked about 1 meter layer thick things. All I can say is in situ does not strike me as a good idea. Right, magma composition. So I've already tried to demonstrate to you from the chromites, the Emerson, that you can see the liquid composition. And the standard model for the initial liquid at the Bushveld is a contaminated chromitite. Could be a picrite as well. Those are the initial magma approximately. So a contaminated chromitite. If we look at using melts and we just take chromitite, you can see that the iron number is way too low, although the chrome number is not so far off. It goes up there, that's when plagioclase comes in. But melts is not a good thing to do when you are crystallizing orthopyroxene. At least half of your chrome is going into the orthopyroxene, and melts does not put any in the orthopyroxene. So you have to take that into account, because your chrome is going down fast, twice as fast as you think it is. So you have to do something about that. If we take the B1, which is a chromitite with about 30 or 40%, or it's about 30% upper crust mixed in. That's what Meltz has to say about it. But interestingly, Draga and Brennan, with a recent JPET paper, they took the B1 and actually did experiments with it. And this is the line they get, the red line there. So I'm rather happy with that, because it matches roughly where our chromites are. Oh yes, I should mention there, I've only put the chromites on that have more than 50% chromite in the rocks. The other ones are not on there anymore. You'll notice we don't have this spread over here, and the Marinsky ones were somewhere over here. Marinsky is a different kettle of fish. Not touching Marinsky today. Right, so the experimental work at anhydrous at FMQ using the B1 liquid does approximate natural compositions. The B2 would be too poor in chrome to make the chromites we see. And you could put water in, but when you put the water in, the chromites tend to come out too iron rich. So, but that's partly because when you put the water in, you're oxidizing it. So it makes a bit of a mess of things. What is clear is you can't have chromite and plagioclase crystallizing at the same time. They wouldn't have the right composition. You can have chromite, but then the chromite would, the chrome number should be down here. So you have to crystallize, you have to have the chromite and then crystallize the plagioclase afterwards. But that matches the textures anyway, so no, it's not a problem. Okay, so we're still talking about do the chromites reflect the magma composition? Looking at still water, going through the A, B, C, and even to E, the open crosses are when they're less than 50% chromite. The solid crosses are when the rocks had more than 50% chromite. Now, interestingly, at still water, the layers below G have lower phosphorite content than the layers above G. So the phosphorite content of olivine is 82 to 84 here. The chrome number is going up a bit, but once we get to G, we get the highest chrome number. We also have the highest phosphorite numbers here. So the chrome is reflecting roughly what the olivine is telling us, and it's not changing. The chrome number doesn't change that much. Titanium is very much the same above the G. Below the G, we have higher titanium, but of course we have lower phosphorite. So the magma is much more, or appears to be somewhere in here. The magma has changed to be more primitive, or there's less contamination, whichever way you want to look at it. Or Alan has some other explanation that I'm sure he can give us. The vanadium and the gallium don't change that much. When we come to the bushveld, and this is not to scale here, I've just put the chromites here on top of one another. But the point is, if we looked at the Mg number of the orthopyroxene, it generally goes down in the lower critical zone. The chrome number also goes down, and the gallium goes up, and the vanadium goes up, which is exactly what we expect, because as the magma gets more fractionated, these concentration of these elements go up, and so that's all coherent. Once you hit the upper critical zone, you see the magnesium number here doesn't wobbles all over the place, but it's roughly the same all the time. And the same is true of the chrome number. It's rough, it's very similar, the gallium and the vanadium. So in this bit, it's much more evolved, yes, or it's more evolved, but it's not changing that much. So it's the chromite is reflecting the magma. Okay, composition of the liquid. So this is a spidergram to try and look at your trace elements. And what I've done here is I normalized to the chromatite chromite, because the chromatite chromite is probably the most primitive thing we're going to see. And these are all the chromatites like that, fairly flat. And we have a bononite here, because a bononite is sometimes also proposed as an initial magma. Compared to bononites, the bononites are fairly depleted with tin, hafnium, and titanium, a little bit with gallium. If we look at the Great Dyke, compared to the Great Dyke, the dunite succession towards the bottom, the patterns are fairly flattish and too enriched in things like tin, hafnium, titanium, and gallium to be from a bononite. In the bronzite section, the upper part of the section of the Great Dyke, you'll see you've got negative scandium anomalies. And that's because pyroxene is now on the liquidus. Pyroxene is taking the scandium. So you can use that to tell whether you've got pyroxene going. If we look at still water, again, it doesn't seem to match a bononite. And we've got these big negative scandium anomalies. Now, some of you are going, no, can't have scandium anomalies due to pyroxene, because it's olivine. but it's still water. But there are large orthopyroxene oikocrysts along with the olivine. So the chromite is sensing the orthopyroxene that is present. It's usually 10 to 20% orthopyroxene present of the silicates. I mean, you got 90% chromite, but you still got that going on. Bushveld, I'm only going to show you the lower critical zone here. Again, you see the effect of the pyroxene crystallization here, and doesn't really look like a bonanite. I'm guessing it's contaminated chromitite. Okay, so why we're back to PGs. Why were we doing this in the first place? We wanted to know about PGs. Now, if you look at the lower critical zone and we look at the chromites from the Bushveld chills, the chromites would match it. But when we analyze the LG1 and LG4 chromites, they don't contain any PGs. It's basically the detection limit. So although volcanic chromites contain IPGs, most of the time, the layered intrusions do not. That's because it's usually in laurite or some PGM, which Malta's going to tell you about in a minute. And when we look at the platinum palladium, yes, we could match everything for the chills and then add a bit of sulfide. But again, we don't have, if that's the whole rock and that's the chromite, we have a problem. We have to do something else. We have to get the PGEs out of the chromite into the various PGMs and sulfides. How's the time? Okay, right. So this is probably the most controversial bit. So you can put your fingers in your ears if you're not interested. This is our experiment. Here is supposed to be the margins of the intrusion where you have a bit of chromite, which is in red. The black, confusingly, is plagioclase, and the white is pyroxene. And that is because you have to get the right density and right size of beads, and you don't get to choose the colors. So there's an analog experiment where we actually made sure the viscosity of the glycerine is the right viscosity to approximate the viscosity of a scale. It's a scaled experiment. It's not just we just took some beads and tried. It actually all fits together. Right, so that's supposedly the magma chamber. Then here is a little plastic gate. You take the gate out and things run down, the grain sorting that Steve was mentioning. And notice the thickness of the bed changes as you go down along. So you would expect as you go into the chamber, the thickness would vary or along the chamber. Right. Things don't stop there. You can crystallize some more chromite if you like. You can do all sorts of things. We're just collecting it up. Game isn't over. We have not solidified. As pointed out, you need at least 30% liquid to move the slurry. Lots of things can happen afterwards. And one of the interesting things about this is if you repeat this, depending on how solidified the section was, you can inject one chromite into another and thicken the bed. So the first time you've got a couple of centimeters, and then if the bed has not yet solidified, the next time there's an earthquake and things slump in, the chromites inject into the bed that was already there. And so you thicken the bed. And as you go across, you can get some fairly complex stratigraphy going on here, depending on how solidified things were. Okay, I'm not going to go through the conclusions. I'll leave the time in case somebody wants to ask some questions. Yes, Steve.
Okay, right, sure.
His problem.
The thing I have a problem with is your claim that you're substantially changing the chrome number of your chromite due to some sort of post-cumulus reaction. And I don't think it's possible. And the reason is that because your chromite is such a dominant repository of chrome in the rock. So if you've even got 10% chromite in the rock, that's 5% Cr2O3, right? So that's much more than chrome in any of the other components in the rock. If you're going to change the composition of the chromite,
It's the aluminium.
well, all right, but you can't just change one or the other because you've got a closed system. Right? Let me finish the argument. So if you're going to change, so all right, so if you change the iron, you can change the iron and magnesium because you're exchanging it with the silicate phases. You've got an exchange reaction. Iron and magnesium in one exchanges the iron magnesium in the other. You don't have another phase with enough chromium in it to be able to substantially influence the chrome content of the chromite. You can do it's just a Lieberall calculation. It's easy to do.
I understand what you're saying.
So let me finish the argument. Then Josh should shoot me down. But just to I mean, particularly at 50% chromite, there's no way you can touch the chrome content.
No, not trying to do it.
I've done the calculations. I don't think you can do it even down to 5% chromite, but we could argue about that. So my contention would be you're not changing the chrome content of the chromite at all. That's the chrome number that you're seeing is the original magmatic value. And what you're seeing is a variation in the primary composition of the chromite, which is related to the mode, which is related to the deposition mechanism, which is the argument that Barbara Merck made in her paper, where she showed exactly the same thing anyway. So that's the question is, if you wanted to get around that, what are you exchanging the chrome and aluminium with in order to satisfy that mass balance problem?
I didn't change the chrome. Assuming chrome constant.
Well, no, but hold on. But in the earlier, sorry. All right. Well, you're assuming it there, but earlier on, and but just before that, you were saying that the chrome content of the chromite is changing, and therefore you can't trust it in the lower, in the lower chromite abundance rocks. So you said that, but then yeah, exactly, yeah. So how do you know that chrome number, or Cr2O3, however you measure it, how do you know that's not just the original chrome content of the cumulus chromite? It hasn't changed at all.
Well, this isn't my data, but I suppose you could say for the bottom of the LG6, the same problem. Because it's right next to the ones that are okay, 1 centimeter away. And because, yes, you've taken the chrome number down, but look, you've taken the titanium up by 50%. How are you going to suddenly have the titanium at 50% more? Where's that titanium coming from?
Well, the difference is there's titanium in the other phases of the rock.
Yeah, but
so so if you look at the partition coefficient for chrome into chromite, it's like 100.
Yeah.
The titanium, it's way less.
Yeah.
So you don't have the same mass problem with any of the other components. It's only the chromium that's the problem.
That's why I did that graph and said, okay, keep the chrome constant. What else happens? Now it's the aluminium that is going down. And that's what the Coutard showed in the experiments. Aluminium goes down, chrome stays the same. So the chrome number changes. And the reason chrome looks lower is because you've added 13% mass with the iron adding. So you're adding iron into the situation. You've got a higher iron number.
Yeah, but the chrome number is chromium, not the chromium. So that's not affected by the iron.
Okay.
Okay. Sarah, about that diagram with gallium and vanadium, which is then the same. And
what would you like?
I think that the simplest explanation for this, I think basically you proposed it yourself during when you were discussing with Steve, when you said that the Bushveld complex is not a closed system. It's basically a lot of magma got out of this system. It basically flows through system. And if we accept that, that means that magma is flowing, crystallizing, and that's why there's no change. And that is the same explanation which is used to Stillwater complex to explain why there's no Mg number change in this ultramafic zone. It's always the same. So it's not just the problem of chromitites, it's these paraxenites all living the same thing. They're not changing at all. So I think the answer is perhaps the flow through system, or otherwise we can bring crystals, cargo all the time, which I don't like very much.
I know you don't like it very much,
Yeah,
but the point is if you have in situ crystallization
yeah,
of chromite and you've only got chromite on the liquidus,
yeah.
those elements should go down.
Yeah, if
they're not doing it.
if in a closed system, you're absolutely right. If it's closed system, but if it's magma is coming and flowing, then it will be the same. And about the experiments, which I always look, I just look at once again, you know, in the rocks, when you look, all these minerals are kind of penetrating each other. There's, you know, they're hugging, kissing, loving each
Yeah,
other in
that's
the
what
rocks.
happens afterwards.
And yes, and you are separating them. It looks like it kind of not humanistic to me. Sorry. Thanks.
Okay. But the subsequent processes can do all sorts of things,
Yeah.
which I've only taken it so far. Yes.
We were investigating UG2 from Cardiff mine, and there you have a hell of differences in chemistry, and the chemistry is changing according to the host. You have much higher alumina in the plagioclase host,
Yes.
and less magnesium number, and this increasing in the autopyroxene, and is completely different in the chlorophytes. And in the
Yes,
chlorophytes, you
yeah.
get almost rid of all the titanium.
Once you're in the silicate rocks, yes, it will change. Great. No problem.
Other questions there?
Ah, okay, on the back.
Is it inferred from your data that accessory chromite in bushveld is enriched in PGEs while chromite in chromitite is depleted? Or am I right? Did I understand correctly?
Sorry, I wasn't quite clear there. The chromite in the bushveld chills, the dikes that inject, the IPGs do appear to be in the chromite. But in all the other chromites we looked at, whether they were disseminated or massive, we had no PG. It was less than detection limit of PGs in the chromite.
So from this, it is inferred that the IPGs rapidly form their own phases.
Yeah, this is another controversy.
Mhm.
You could do as somebody, I think it was Brian showed us pictures from, or maybe it was Steve, Brennan's Finnegan's pictures where you've got the IPGs in the boundary layer.
Okay.
That's one way to do it.
Mhm.
But what I like to do, and it's not very popular, is say they were in the chromites, and then when sulfides is a little bit of sulfide is added to the massive chromite layers, and during sintering and so on, the IPGs diffuse out of the chromite into the sulfides and make laurite.
Okay, but at least in the chilled margins, the IPGs form an isomorphic admixture in chromite, right?
The euhedral chromites in the chills. Is
Mhm.
it? Yes.
Yeah, okay, thank you.
Anybody else? Good.